think Ellie had one, right? Number 4. And that is on centroids. Is that right? Okay, so number 4 on centroids. Okay, so this distance is 0.1 meter. This is 0.1 meter. This is 0.3 meters. This is 0.2. This is 0.4. And the whole distance from, let me just extend these. This is another 0.1 meter. So that's the dimensions. And then at the middle of this long part of this shape is a pin joint. And that's the connection to the wall. And so that means that this, the distance between here and here is 0.05. The object has a mass of 200 kilograms. And we want to find the reaction joint at the pin, the reaction force at the pin joint, and the force vector that the cable applies to the object. So the first thing is a free body diagram. Well, maybe before I do that, let's calculate the centroid, because we're going to need that centroid to calculate where the weight force is applied. And let's put our coordinate system right here. That's also a good place to put the about point, and sometimes it simplifies things if your origin and your about point are at the same spot. Okay, so for the centroid, I'll break it up into these 2 rectangles. I'll call this the first one, and this the second one. The origin's over here. And so for rectangle 1, the area is 0.1 times 0.3. So 0.03 meters squared. And the centroid in that coordinate system that's shown is 0.15 meters in the positive x direction, and then 0 for y. And those units are meters. And then for the second rectangle, the area is, let's see, it has a height of 0.2 and a width of 0.2. So 0.04 meters squared. And then the centroid, it's going to be right in the middle here. So to get from here over there, you have to go 0.3 meters to get to this side, and then another 0.1 to get to the middle. So that's 0.4 in the positive x direction. And then for y, we know it's going to be 0.1 meters down from the top. Well, this is 0.05 meters down from the top, so it's another 0.05 meters down. So the y position is negative 0.05. And then the total area you get from just adding those two up. So that's 0.07 meters squared. And then the centroid, the total centroid, is 1 over 0.07 times the centroid of rectangle 1 times its area plus the centroid of rectangle 2 times its area could someone calculate that? Or does anyone have it? .293 negative what? 0.02029. 0.029. Okay. Now that's where the weight force is going to be applied. Now let's do a free body diagram. At the pin joint over here, we know that there's a full force vector. I'll call that RA. And then the weight force is somewhere over here. That's right around where the centroid is. Notice that it doesn't matter with a weight force where you put the, any vertical force. It doesn't matter vertically where you put that location because you can move that force anywhere along its line of action. Mass was 200 kilograms, so this is 1962 newtons down. And then the cable force points this way, I'll call it T. And before I go on and fill out the table with the row values and force and moments, let's calculate the force vector applied by that cable. So the vector that we want, well, the force vector we know is going to be pointed this direction, from this point towards the wall. And we know the magnitude is going to be T. So we want a unit vector that points in that direction. So if we can come up with a non-unit vector, just any vector that goes in that direction, then we can normalize it, divide by its magnitude, then multiply by t, and then that's our force vector. So a vector that goes in this direction goes 0.4 meters in the positive x direction and 0.2 meters in the positive y direction. So this vector u is positive 0.4, positive 0.2. The magnitude of that is 0.4 squared plus 0.2 squared, square root. And so could someone calculate that unit vector?
Four.
0.447, 0.894. No. The other way, right? 0.894, 0.447. Okay, and then the force vector applied by the cable, I'll call it force cable, is this times t. So 0.894 t, 0.447 t. Now I'm going to write out that table. Row vector, force vector, moment vector. First, I'll do the force RA. The about point I'm going to use is the origin. So there's no row vector for RA. The force vector is RAX, RAY, and cross product is 0. Then the weight force. Whenever you have your about point at your origin, the row vector is just the coordinates of the point. So we know the coordinates of the centroid, that's a row vector. Whatever that was, 0.293, negative 0.029. The weight force is 0, negative 1962. And what's that cross product? $574.9. Negative. Okay. And then the last one is that cable force. The coordinates where that cable force is applied right here is 0.5 meters in the positive x, and then 0.05 meters in the negative y. So that's the row vector, 0.5, negative 0.05. And the force vector is what we just got, 0.894 t, 0.447 t. And let's see. I don't know. Could someone calculate that? 0.2682. Positive t. Okay. So now we'll use Newton's second law. Add up all the forces. RAX, RAY, plus 0, negative 1962, plus 0.894 0.94t, 0.447t is equal to zeros. And the moment equation says negative 574.9 plus 0.2682t is equal to 0. And so you can use the moment equation to calculate t. What's 574.9 divided by 0.2682? 2143.4. Okay. And then plug that into the other equations and you can solve for RAX and RAY. Can someone tell me what those are? Yeah. 1004? Okay, newtons. Any questions about that? Any other homework problems you'd like to see? The distributed loads? Yeah. Well, I will talk about that some next, and then maybe I'll do one of those after I go through it. Any other questions? Okay, so the idea with distributed loads is instead of a force being applied at a point, it's spread out over an area or a distance. Yeah, that's right. So you treat it like a point force that acts at the center or the centroid of the shape. So it's a force that's spread out over an area or a distance. In fact, really point loads are the things that don't exist. No matter how close to a point load it is, if you magnify enough, that force is spread out over some area in 2D over some distance. The way to think about it, I think, is, so I'm going to make this little table that sort of compares the relationship between distributed loads and point forces. To the relationship between instantaneous speed and distance traveled. Okay, so first of all, a distributed load doesn't apply a force at any single point. A distributed load doesn't apply a finite force at any point. At any single point, it's an infinitesimal force. And you can think of that in the same way that, like, if you think of you're going a certain instantaneous speed, well, how much distance have you traveled at a single instant, If you're going 50 miles an hour, at a single instant, you don't travel anywhere. It's an infinitesimal distance that you travel. In order to travel a finite distance, you have to carry speed over some finite interval. And it works the same with this. So an instantaneous speed doesn't travel any finite distance at a single instant. Sorry, let's make this number 1. These are all supposed to be like sort of comparisons between the two. Number 2, to produce a finite force, a distributed load has to act over a finite distance, over an interval of distance. Just like in order for an object to travel a finite distance, it has to have, it needs to carry its speed over some finite interval of time. So to travel a finite distance, you need to have the speed over a time interval. And the third relationship is a distributed load says how much force would be applied if that uniform distributed load was spread out over a full meter. And you can think of that as exactly the same idea as the instantaneous speed says how far you would travel if you held that uniform speed over a full second or whatever unit. Okay, so for example, if you're going 50 miles per hour and you hold that speed of 50 miles per hour for a full hour, you're going to go 50 miles. If you're going 30 meters per second and you hold that for a full second, you'll go 30 meters. The idea with a distributed load is if you have a beam and a distributed load like this, let's say that this length is 1 meter, and this distributed load is 2,000 newtons per meter. And that means that the total force applied is 2,000 newtons. Any questions about that yet? To do calculations involving distributed loads, we're going to always have to represent these distributed loads as point forces. So we'll need to represent these as point forces. And there's two things we know that we have to know in order to represent these as point forces. So we need two pieces of information. First is how big that point force has to be, the magnitude of the point force. Well, you would actually need to know the direction of the point force too, but for us, these distributed loads are always going to act straight down, so the point force is always going to act straight down. But the other thing we have to know is where that point force is going to be applied. Okay, so let me make up an example. So let's say we have a beam with a length of 3 meters. And let's say that the distributed load has a triangular shape. And at the maximum, let's say that that's 10,000 newtons per meter. And I'm going to calculate the magnitude of the point force and the location where we'd have to apply it in this case. So first, the magnitude is the total area of the distributed load. In other words, I mean, what you're really doing is integrating this distributed load function over x. So in this example, the numbers are going to look a little funny because they're obviously sort of on very different scales. But you can think of the width as 3 meters. You can think of the height as 10,000 newtons per meter. Calculate the area of a triangle. That's base times height over 2. So that's 3 meters times 10,000 newtons per meter over 2. And notice that the units work out. You cancel this meter with this meter, and you get units of newtons for the magnitude of the force. And in this case, that's 30,000 divided by 2, so 15,000 total newtons. And then the location where that force is applied is the centroid of that distributed load. So the location is the centroid of the distributed load shape. For a triangle, if the length is 3 meters and the height is 10,000 newtons per meter, centroid is over here somewhere. And that's 1/3 of 3 meters from the right side, from the wall side. So this distance is 1 meter. This distance is 2 meters. One thing to notice here about the location of that force, notice there's never any need to find the y position of that centroid, because the forces of our distributed loads are always going to be acting down. So you can move that up and down along its line of action anyways. So the vertical location of the centroid won't ever matter for us. Okay, so let me do an example problem. Let's say we have a beam that's a cantilever at the right. And let's say that it's subject to a distributed load with a triangular shape. The maximum value is 10,000 newtons per meter. And the width is 2 meters. And we want to calculate the reaction loads at the wall. The first thing we have to do is represent that distributed load as a point force. So let's think about this distributed load shape, this triangle. It has a width of 2 meters and a height of 10,000 newtons per meter. So the area is 2 meters times 10,000 newtons per meter divided by 2. And so the total force is 10,000 newtons. That's just a coincidence with the numbers I use. There's no automatic relationship between the maximum of that distributed load and the force. You have to calculate that area. And then the centroid. So the centroid is going to be here, and we're looking for the horizontal distance, let's say from this edge. Well, that's going to be 2/3 of that 2 total meters. So this distance is going to be 4/3 meters. Any questions about that? Yeah. That's right. Yep, that's exactly right. Yep. So just go to the table of shapes, and we're just calculating where the centroid is for a right triangle in this case. And it's always 1/3 of the way from the wall, 2/3 of the way from the point. Yes. Mm-hmm. Yes. Yep. You just add that as another force. Yep. We'll do some like that. So why, in this case, I ignored the weight of the beam. Like, why would you do that? Yeah, exactly. So in this case, maybe the mass of this beam is 20 kilograms or something, and compared to the force of 10,000 newtons, that downward force of 196 newtons or whatever, we'll just leave it off. It doesn't add much to the answer. Okay, so now that we have these, we can draw a free body diagram. We know that 2/3 of the way along the beam, from the left to the right, we're going to treat it like there's a point force here. And it has a magnitude of 10,000 newtons. And we know that this distance is 4/3. And then the only other loads are the reactions at the wall. So with a fixed joint like this, what are the reactions? That's right. This is in 2D. Fixed joint limits, doesn't allow any degrees of freedom. So you need 2 components of force and 1 component of couple. Okay, so we have an unknown force vector. I'll call that R. And we have an unknown couple. I'll call that reaction moment, MR. And now we can, it's when you're dealing with beams like this, horizontal beams, which we're going to do a lot, it's not too hard to just eyeball what these moments are. So I'm going to do this 2 different ways. Okay? I'm going to first do it with the rho and the force and the moment, and then I'm going to show just how to do it sort of in your head. But so rho, force, moment. And let's put the about point over here because that's where we have the most unknown forces. Okay, so if the about point is at the wall, then for the force R, the rho vector is 0. The force vector is RAX, I guess it's just R, RX, RY. Cross product is 0. Then we have that couple MR. So for couples, we don't care about this stuff, and we just add it over here as a moment. Then we have the 10,000 Newton force. The rho vector, well, I guess since our about point is over here, the distance we really need is this. The whole thing is 2 meters. This part that we don't care about is 4/3, so this is 2 minus 4/3, so 2/3. And so the rho vector is negative 2/3. Force vector is 0, negative 10,000. And take the cross product, and you get positive 6666.6 repeat. Now Newton's second law says Rx, Ry plus 0, negative 10,000 is equal to zeros. So this vector R is 0, positive 10,000. And the moment equation says MR plus 6666.6 repeating is equal to 0. So MR is negative 6666.6 repeating. The units are Newton meters for the moment for that couple, and for R it's newtons. Okay, so now let's look at this picture and just try to make sense out of the signs of this stuff, make sure it makes sense. Does it make sense that over here you'd have to apply a 10,000 force up? Yeah, because it has to counteract this 10,000 force down. And then for the couple, does it make sense that we would have to apply a clockwise couple at the wall to keep that in equilibrium? Yeah, because if this is the about point, this is going to try to make it go counterclockwise, positive. So the wall has to counteract that with a negative couple. Okay, let me show you sort of a quicker way to think about this. Eventually, I think all of you will want to switch to doing it this way when you have horizontal beams. So a quicker approach for horizontal beams. You can use this idea on anything. It's more useful on horizontal and vertical things because it's easier to calculate these distances and things. Okay, so let me draw this free body diagram again. We have this force R, the couple MR, and this downward force of 10,000 newtons. And we know that this distance is 2/3. Okay, so I'm going to go right to Newton's second law. We have a downward force of 10,000, so that's 0, negative 10,000. And we have the force vector Rx, Ry. Those add up to 0. So this force vector R is equal to 0, 10,000. Now we're going to do the moments. And in most problems, it's nice to write out that row force moment table because row vectors are sort of complicated. Notice that in a case where you have horizontal beams, nothing's complicated about those row vectors. Every row vector is just totally horizontal. And every row vector is totally perpendicular to the vertical components of the forces. So for the moment equation, Rn2L, we have the couple, Mr, our about point. I'm going to still use the same one. There's no moment produced by R. And then for the 10,000 Newton force, you just have to think, what's the moment arm for that 10,000 Newton force for this about point? We know the distance is 2/3, so that's what it is. So moment arm of 2/3 times the force, in this case 10,000. And now instead of thinking about the signs of the row vector, just think about which way this force would make this body rotate around the about point. In this case, a downward force of 10,000 would make it rotate clockwise, counterclockwise, so positive. So this is positive, counterclockwise. And it saves you the time of writing out that whole table, calculating the vectors and stuff. We get the same answers. That's good. It's not very useful if you get different answers. Any questions about any of those? Let me do one of the homework questions. So centroids number 5. It looks pretty much like the one we just did, but the cantilever is on the other side. So we have this beam. We have a distributed load with a maximum of 8,000 newtons per meter. And the length is 1.5. And we want to calculate the reaction loads at the wall. So first, let's calculate the centroid and the, well, you know, we want to represent this as a point force, so we're going to calculate the total area and then the centroid. The base is 1.5, the height is 8,000. So the area is 1.5 times 8,000 divided by 2. So that's 6,000 newtons. And then the centroid is 2/3 of the way from the left corner to the center, 2/3 of the total of 1.5. 2/3 of 1.5 is 1 meter, so this distance is 1 meter. And I'm going to put the coordinate system here. And now, free body diagram. At the wall, we have a force vector, R, and a couple MR. And then we have a downward force of 6,000 that's produced by that distributed load. And it's at a distance of 1 meter from the wall. So you could write out the table now, calculate the row vectors, force vectors, moment vectors. I'm going to just do it that other way. So Newton's second law says Rx, Ry plus 0, negative 6,000. Oh no! You know what? I forgot something in this one. It also includes a weight. Okay, so the mass is 75 kilograms. So we calculated the stuff we need for this distributed load. We also, in our free body diagram, have to include the weight force. So that acts right at the center. And it has a magnitude of 75 times 9.81, which is 735.75. Okay, so Newton's second law, R, and then the force from the distributed load, and then the force from the weight, which, by the way, is also a distributed load. We just all along have been treating that like a point force, so we don't have to recalculate it. So that's 0, negative 735.75. and those all add up to 0. So the R vector is equal to positive 6,735.75. Well, the y component. And then the moment equation, we'll put the about point over here. So we have the couple MR. We don't have any moment produced by that force R. Then we have that force of 735.75. What's the moment arm for that? Okay, so I'm going to write this all in here. So the moment arm, that's acting right at the midpoint of that beam. So the moment arm is going to be 0.75. The force is 735.75. So I just wrote both of those as positive. And now we'll think about the direction of the rotation that produces. So if the thing rotated freely around this point, you apply a force like that, would it rotate clockwise or counterclockwise? Clockwise, so this is negative. And then the moment arm for the 6,000 is 1. I'll do the sign in a second. Force is 6,000. And would that make it rotate clockwise or counterclockwise? Clockwise, so that's negative again. And those all add up to 0. And so the reaction moment is, what did you get for that? So the whole thing will just be 6,000 plus that, so 6.8 positive, and that's Newton meters. Okay, so I have a question, sort of an intuition question. So we had this problem with that distributed load starting at 0 at the wall and then growing to 8,000 newtons per meter at the far point from the wall. What do you think if we had this same setup, but the distributed load was acting so that it was at 8,000 newtons per meter at the wall and 0 away from the wall? You think that would be harder on this joint, more likely for it to break, or less likely for it to break? You know what I'm asking? Yeah. The way it is right here is more likely to break this connection than if that was flipped the other way. And the reason is, it just has to do with the centroid. Like the area of that shape would be the same either way. But this way, the centroid is over here. If that triangle was flipped the other direction, the centroid would be over here. And that means that in the other configuration, the moment arm would be less, and there'd be less of a couple required by the wall. Okay, so let's do that one. And you're going to see that it's surprisingly painful. And I'll point out why. You wouldn't think so. So here's a triangular distributed load. In the other direction. And this way is harder. Okay, so let's do the exact same beam, same connection, but this time the distributed load is like this. where this is 8,000. And the mass is 75 kilograms. And we want to calculate the reactions. You know what? Actually, now that I'm totally mixing this up with a topic in D form. Or this is a topic we're going to go and do later, but no, I was totally wrong about that. This is no harder yet. It's going to get harder later. Okay, so the first thing, let's figure out centroid and the total force. So we have a base of 1.5, a height of 8,000. So the area is going to be the same as it was before. So 8,000 times 1.5 divided by 2 is 6,000. And the centroid location is half a meter. And now free body diagram. So we have the loads at the wall. That's a force R and a couple MR. And then we have the weight force acting in the middle at 735.75. And then we have the force from the distributed load. That's 6,000 newtons. And that's acting at a distance of half a meter from the wall. So Newton's second law says Rx, Ry plus 0, negative 6,000 plus 0, negative 735.75 is equal to zeros. And so R is equal to 0 for X, positive 6,735.75 for Y. So how does that compare to the force that the wall was asked to apply in the last one? So the force is the same. The thing that's going to be different is the couple. And then the moment equation, we'll use the same about point we did last time. So we have MR, and then we have the 6,000 Newton force with a moment arm of 0.5. Is that clockwise or counterclockwise? Clockwise, so that's negative. And then we have the moment arm of 0.75 and the force of 735.75. And is that clockwise or counterclockwise? Clockwise again, so negative. And so this time we get MR of 3,000. What was it before? 551.8. So 3,551.8. Newton meters. And so if you set up if you have an engineering application where you're setting up something like this, you don't need as strong a connection to the wall as you do in the case where the distributed load is getting bigger as you get farther from the wall. Yes?
As we get farther into the material, we're going to get questions like, will this join?
No. You know, if you take deform from me, we'll start to get into some questions like that. And even when we start to get into internal loads, we'll start to do calculations where you can kind of get towards that. But obviously, like whether something's going to break or not depends on the materials you're using. And so we're not doing any calculations that are any different for wood than they are from steel or whatever. In deform, we'll start to use the parameters that define the different materials. Any other questions? Okay, let's stop. Go sit in the sun. Okay, see you Thursday.